Hello, welcome to today's lesson. Like I said, today's lesson will be a continuation of the previous lesson, which was this. This was our example for the previous lesson. And today we'll be diving into introduction to load flow analysis. Now, for those that are new to the channel, you're welcome. Please click the like button, smash that subscribe button, and also turn on the notifications so you get notified immediately I upload a new video. Now, diving into today's business, we are going to talk about load flow analysis. But before we begin running the load flow, I think it's necessary to know what load flow is all about. So, load flow analysis is a study that provides a systematic mathematical approach for the determination of various bus voltages, their phase angles, active and reactive power flow through different branches, generators, and loads under steady state conditions. Now, I'm going to be explaining that gradually. So now coming to run the load flow, if we click run, this is the run load flow. Now we see this. When we talk about the various bus voltages, this is what we mean, this 100% and 99%. Okay, remember from our load flow toolbar, this is percent voltage. Now this is just for the voltage. It can actually be in any unit. If you click and hold, you can change it to kilovolts or volts. Now, as it's in volt, notice the value has changed to 13,800, but when we take it back to kV, 13.8 kV. Remember, the bus 1 nominal kV is 13.8 and it's still 13.8 kV here. Now, bus 2 nominal kV is 4.16 kV, but here the operating voltage is now 4.12, which means there was a voltage drop here. Now, load flow analysis helps us to identify voltage drops. So let's take it back to percent voltage, as I think that's more efficient. So you can see 100%, 99%, I mean there was a 1% voltage drop at bus 2. So next, active and reactive power flow. Now this, as we all know, this is the real and this is the imaginary. This is where we can toggle options to show the unit we want to see. Now you can choose your apparent power. This is only apparent power kVA, or you can choose your true power and reactive power, which is kilowatts and kVA, or you can just choose kilowatts or anything you want. Basically, you can see everything, and that's why we carry out load flow analysis. So moving on to today's lesson will be going in on cable parameters and generator parameters. So let's work on our edit mode. Okay, we'll shift this a little bit to the right, and then today's first instruction is to extend bus 2 to the left. Now, how do you extend the bus? It's simply by tapping on it, and then you take the cursor towards the edge of the bus until the arrow changes to something like this, and then you click and you drag. So I think this should be okay. The next thing is to insert a cable. Okay, a cable. I think this should be our cable. Yes. So we click and drag, and then we insert the cable. Now, okay, I think I have a cable at the dumpster. That's why it's showing cable 2. So just go to the cable. Yeah, I have cables at the dumpster. And you delete and you come back. So we'll pick a cable. And yeah, it's cable 1. And then we connect the cable to the bus. After that, after connecting the cable, we pick a transformer, another transformer, a 2-winding transformer to be precise. And then, okay, let's use our auto build. We'll pick a cable to make it faster. We connect a transformer. Now, if we notice, there's a bus automatically inserted between the cable and the transformer. And I'm going to leave that as an assignment for you to figure out why there's an automatic insertion of a bus, a node bus. You know, there are types of buses, node bus, and this one, you know, rectangular. So, a node bus is automatically inserted. I need you to tell me why you feel there was an automatic insertion of the node bus. Now, from the transformer to a lump load. Yeah, this is our lump load. There is another node bus inserted here. Now, why? Now, that's an assignment for you. So, like I said, today we'll be learning cable parameters and generator parameters. Okay, now we can actually reduce the size of this. Let's see here. Yeah, that's enough now. So, for cable, remember, double click to open the dialog box. Now, for the parameters of the cable, we have NEC EPRO 133% copper, 3-core copper, frequency of 60 Hz. Now, let's remember the system we are working on. If we go to projects, standards, we can see that we are working on ANSI at frequency of 60 Hz. So the cable we are using, remember, should be in 60 Hz. Now, the length of the cable is 200 feet. Remember, you can actually toggle this for different units. So, length 200 feet. And now for the other parameters, like I said, I will actually give the parameters for this lesson on the WhatsApp group. So if you're not in the WhatsApp platform, just drop a comment below and I'll add you up to the WhatsApp group. Like I said, the specifications for this, let's go to the beginning so you understand how it actually works. Now, this is the beginning. Cable parameters. The specification says NEC EPR 133%, 5.0 kV magnetic, 3-core copper, and the size is 4/0. Now, length is 200 feet. We have already put that. So now remember, we're in a frequency of 60 Hz, so we will not use a 50 Hz cable. Now we are now in 60 Hz. This is frequency. But from the specification of the cable, we have the kV, which is this, to be 5.0. So all we have to do is keep searching until we get to 5.0. Okay, we've gotten 5.0. Now remember also it says copper. Now this is aluminium for the type. So we have to find the 60 Hz copper 5.0 kV. And we keep searching. Okay, we've gotten to copper, but the kV is not 5.0. kV is 1. Yeah, copper 5.0. Okay, this is one. Now remember, from the specifications, supposed to be NEC EPR 133%. Now the percent phase should be 133, this, and this is 100, so we keep going down until we get to 133. Yeah, we've gotten to 133. So now we've gotten frequency, check, 60 Hertz, the type, copper, correct, the kV, 5.0, correct, percent phase, 133, correct. Now 3-core, supposed to be a 3-core cable, and this is 3-core. Okay, that's good. Then it's supposed to be EPR with the insulation type EPR. That's good. It's supposed to be magnetic. So EPR, but we are forgetting something. NEC. It says the source should be NEC. The cable source should be NEC. So we search for NEC. Oh yeah, this is NEC. But this is 1-core, so it won't work. It's supposed to be 3-core. 60 Hertz, copper, correct. 5.0 kV, correct. Percent phase should be 133, correct. Number of cores, 3 cores, correct. EPR, correct. NEC, correct. Magnetic, correct. So we've gotten our cable. And now for the sizing, it's 4/0. Now this is the sizing. And we can just come here and look for 4/0. Yeah, this one. And then click OK. Click OK. So we are done with our cable sizing. Now for bus 3, remember it's a node bus. So we double click on it, and the nominal kV is automatically 4.16. Now let me explain. If you come to bus 4, the nominal kV is 3.3. Why? Because of this transformer. There is no transformer here that is reducing the kV that is passing through, and that is why from this bus to the cable they still have the same kV. Now for transformer 2, the ratings should be, let's see, MVA of 1 MVA. Let's use 1 MVA. And then for the impedance, whenever you come across an element that you don't know the values, you can see there's a typical here and typical here. If you know the impedance of the transformer, you can put it, and if you don't know the XR ratio, you can use a typical XR. Now, what the function of this typical is to automatically generate calculations that will produce the automatic values required for the rating of the transformer you have set as 1 MVA. Now watch this. If I put typical impedance, this is typical Z and X over R with typical impedance and XR ratio. So once I click it, the values are automatically there for the transformer. So you don't actually have to stress yourself calculating the impedance, the XR ratio. Once you click on it, everything pops up. So basically we are done with the setting of the transformer for now. And then bus 4, nominal kV for bus 4 should be 0.480. Oh, sorry. Oh, let me just go back. I think for easier parameters, it will be best to put bus voltages first. Alright, so bus 4. Now we come back to this transformer, 0.48. We hope the ratings are set. Yeah, we are going to experience a problem because here it's supposed to be 0.480 for the secondary. Yeah, I think that's about all. And for the lump, you see it has already assumed the kV of the other transformer, which is supposed to be 0. Okay, but we're going to use another kV for the lump load. Let's start with MVA. Yeah, I know. Let's start with MVA. Let's use 1 MVA, same with the transformer. Power factor 85%. And the kV should be 0.46, slightly different from the nominal kV of the bus. And 50% motor load, so we take this to 50%. Yeah, 50% motor, 50% static. And then what else are we forgetting? Say okay, and we run a load flow. Let's see, I'm expecting an error. Okay, now we run the load flow. Let me explain this now. When you run a load flow, you're going to see either pink or red. If the elements remain the same color, which is black, then they are actually operating fine. But then if it turns pink, it means it's marginal. Pink means marginal, red means critical. If we observe well, we'll see that this bus 4 is red, which means it's critical. Now let's go to the alert view and see. This is the alert view. Now it will show you bus 4 is suffering from under voltage, which makes it critical. If you click on the report alert view, you see bus 4. It won't show you transformer 2 because it's not yet critical. It's when it's critical to show you on the alert view. So now transformer 2 is either operating on under voltage or over voltage slightly, but can be managed. Okay, so that's all. If you notice now, the percent voltage drop has increased. It was 99, now it's 98. So it decreased rather. The voltage drop is 98% now. It was 99 because we've added additional loads. Alright, now back to the next one. After running the load flow, we extend bus 2 again to the right. Just a little. And then we introduce a generator to the system, so we can just learn about generators today. Okay, this is a generator. We bring a generator here. Now, to rotate an element, there are two ways. You could use your Control Shift arrow. Yeah, where's the point? Okay, this is the point now. So Control Shift arrow until you get it to the way you want. You can also drag the name of the element around so it doesn't interrupt your diagram, and you connect to bus 2. Now for the rating of the generator, you double click, the dialog box pops up. Now the generator should be voltage controlled generator. That's the configuration. As you can see, it's already voltage controlled. Now for the configuration, let me show you. This is on a swing mode, which automatically makes this a swing bus or reference bus, but we'll get to understand that later on. Now for the gen, the rating should be, let's say, 5 megawatts. 5 megawatts. And then for the category, power factor should be 80%. Then for this gen category design, megawatts should be 5 come here and you click and you put 5. Then Q max and Q min. Q max, you come here and you click under it, click Q max should be 5. Wow, you can move here. For Q min, let's put it at 1. And that's basically all you need to know about generators for now. And then we click OK. Let's take it down a little. And then we run the load flow again. Good. Now, we observe something. This generator is actually sending, if you look at these arrows, this one is coming down, this one is coming down. Now this is from the power grid. The ones coming down are from this power grid and from the generator. The power grid is, the bus here is 100%. This bus now that was actually 98% due to this generator now increasing the voltage, the supply voltage, it has come back to 100%. If you notice, the arrow is going up, which means it's sending out. Well, this is a load, definitely it's collecting power. This is another load collecting power. This is the cable, power is flowing through it. Now if we observe, the transformer is critical, the generator is critical. Now let's see the problem. From our alert view, we can see that generator gen 1, which is this, is suffering from overload because it is it's rated 5 megawatts and it's actually operating at 5 megawatts, which means it's just working at its highest capacity. While for the transformer, it's rated 1 MVA and is actually operating at 1.002, slightly higher. That is why it is critical. Remember, red is critical, pink is marginal. So I'm going to send the parameters for this so you can actually run it, and I'll see you in our next lesson. Stay tuned.